Hello. So today we're going to talk about how the electron configuration that we have already been learning about in class relates to the periodic table. We know very little about the periodic table, but we know that it is a list of approximately 120 elements, and that each element has its own particular set of characteristics based on the number of protons. And we've been able to identify things like atomic number, atomic mass, atomic symbol, all of these things. Now what we're going to do is we're going to relate the information of orbitals to the actual periodic table. So how is it that we can read the periodic table in a very organized way and use it as a roadmap in order to distinguish where these electrons would be found in the electron cloud? Very easily, this can be done if you look at the periodic table in blocks. So I'm going to demonstrate what that looks like in this class. In the beginning of this video, we're going to review some of the things we've already been talking about. But if you don't understand that portion, it's going to be very difficult to relate this to the periodic table. So please make sure you are asking questions, just having those conversations in class. It's really okay for us to stop and talk about those things, but I don't want to move forward if we're still very confused. As a review, we have been doing orbital diagrams and electron configuration. So a reminder, for electron configuration, we use what's known as Aufbau's principle, and we fill from the lowest energy level and then work our way up. So in Aufbau's principle, you'll see this little chart here where we start with our 1s extending into 2s, 2p, 3s, so on and so forth. And as a reminder, the s sublevel can only hold 2 electrons. The p sublevel can hold a max of 6, The D sublevel can hold a max of 10 electrons, and then finally the F sublevel can hold a max of 14. Those elements that get into the F sublevel, those are the ones that have that higher energy level. They are going to have much more going on, and a lot of times these are the ones that are going to be pretty reactive and pretty bad for us, as in like when we're dealing with them in the lab or anything like that. In this class, we won't deal with those types of elements, but just keep that in mind that as you increase into those different energy levels, you're going to see a lot more action, if you will. Reminder, the second principle is Pauli exclusion, where we talk about how every single orbital can only hold 2 electrons max. So any atom can have a huge number of orbitals. However, each individual orbital can only hold 2 electrons. And then finally, we have Hund's rule. And Hund's rule talks about how if we do not have to share orbital space, we will not. As when I say we, I'm talking about these electrons. So you'll see that these electrons in the 2px, 2py, and 2pz, they are in individual orbitals until we have to actually share. So until electrons become too much. So we know the 2p space can hold a max of 6 electrons. If I only need 3 in the 2p space, I would separate them out. If I need 4, I would then go ahead and add in an arrow to the first orbital, leaving the second and third orbitals singles. I also want you to understand that, and a reminder that these need to be opposite of one another. So that is also a part of Hund's rule, that if 2 electrons are sharing an orbital space, they will be opposite. Again, this is all a review from what we've already been doing, but if there are any questions, please make sure to ask me at the end of the video. One other review, electron configuration notation. We know that by using Aufbau's principle, we can distinguish the electron configuration. Basically, you could tell me exactly where these electrons are located within the orbital space in order to identify how reactive they would be. We've also talked about valence electrons very roughly. And as a reminder, valence electrons are the electrons that are found in the outermost energy ring. These are the electrons that will determine how elements will bond. These are the electrons that determine what cations will we make, what anions we will make. So valence electrons are pretty important, and we can distinguish the valence electron numbers based off group numbers. Group 1 have 1 valence electrons. Group 2 have 3. Group 2 has 2 valence electrons. Group 13 has 3, and then 14 has 4, 15 has 5, 16 has 6, 17 has 7, and finally group 18 has 8 valence electrons. We also know that 8 valence electrons is a really good number. That's the number everybody strives for. We will continue to talk about Bohr's diagrams as we lead into the next unit towards the end of this particular unit. And again, as a reminder, we use sublevels and superscripts. So we would write electron configuration like 1s2, 2s2, so on and so forth. And these numbers at the top, these superscripts, represent the total number of electrons. The very last number at the end, if you're in an S or a P, will determine the number of valence electrons. And I'll talk about that here in a minute. So noble gas configuration, we talked about this yesterday where we said that this is a shorthand expression. Using the noble gases in the row above of any element, we will express the notation of an individual atom. So the noble gases found in group 18 are very special because they have 8 total valence electrons, meaning that they have a full outer shell. They don't need to take any electrons from anybody. They don't want to give anything away. They are very much okay by themselves. Now, why everybody wants to look like them is because they're super stable. Stability is favored in nature. So you're using the least amount of energy, and that's what every single atom, every single thing in the planet wants to be at, that stability, that less chaos there. So we use noble gas configuration, and how we do this, we put a noble gas in brackets. So I'm just going to use neon as an example. And if I am doing the noble gas configuration for something like aluminum, which is element number 13, I would just continue to write the last part of the configuration that doesn't include the configuration for neon. So neon, we know that configuration is 1s2, 2s2, 2p6. If we were to do this for aluminum, we would have to then continue to write the total configuration, 1s2, 2s2, 2p6, continuing on to 3s2, and then finally, I don't have enough room, 3p2. This part is a repeat of neon, so that's why I put neon in brackets there, and then I would include at the end here, this should be 3p1, sorry, not 3p2. I would include at the end of neon, I'm going to erase because this is kind of a mess, I apologize. At the end of neon, I would just include the last part that wasn't a part of neon. So it would be 3s2, 3p1. Now, one thing I want you to notice is at the end here, my S and P, I would count these up. That is 3 electrons. That tells me that aluminum has 3 valence electrons. You would only count the electrons for the S and the P blocks. And I'll show you what I mean by blocks here in a second. But I want you to keep that in mind. You only count them for the S and the P blocks. All right, in the next slide, I'm going to talk about those blocks on the periodic table, and then we're going to actually talk about how to read that in class tomorrow. All right, here's a very generic periodic table. It's kind of small, so it's going to be a little harder to write on, but that's okay. Let me see if I can zoom in. I can. Oh, I'm just kind of a mess today, so hopefully that's okay. Okay, sorry, that was an awkward pause. All right, so we're going to identify the blocks here, like what this actually looks like when, I know you guys have noticed, like I can look at the periodic table and then tell you exactly what the last sublevel and superscript will be. And all I do is I just count and know the blocks of the periodic table. So groups 1 and 2 are going to be, that's going to be a little confusing if I don't circle it perfectly. Groups 1 and 2 are known as the S block. Now, reminder that the S sublevel can hold a total of 2 electrons. There are 2 groups here. So that means group 1 would be S1, group 2 would be S2. Now, how do I get the next part? How do I know, like if it's 1s, 2s, 3s, 4s? Well, there are a total of 7 rows here. There are a total of 7 rows here. That means that hydrogen and helium are a part of the 1s. Hydrogen would be 1s1, helium would be 1s2. If we go down to the next row, we have lithium. This is what starts the 2s1, 2s2. So reminder, we're going to read this like a roadmap. We're going to go through the first. That's what off-boss principle tells us. We have to go through the lowest energy level first, and then we move down to the second row. And then we continue reading this like a roadmap all the way down to group 18. So that's the first block. The next block, and this makes up what's known as the representative elements, is this block here. Oh, that includes this bottom part too. This is known as the P block. Now, again, a reminder, the P sublevel can hold 6 electrons. If you count the total number of elements here, it is 1, 2, 3, 4, 5, and 6. That is not a coincidence. So if I were to go through this whole thing, I'd be 1s2 all the way to helium. Then I would go down to 2s, making my way down this whole thing, 2s1, 2s2, that's filled. Now I'm going in here to the P block, 2p. So boron would be 2p1, carbon would be 2p2, so on and so forth. That leads me to my next group, 3s2, 3p6. Now, what you're going to notice about the fourth row or fourth period is that there is now a new block. This block here is known as the D block. And the reason why that's the D block is because they're considered the transition metals, but they have a lot more going on. If you'll notice that we have that step down on off-boss principle, we talk about the 3D sublevels. So we go from 4s, if you look at your filling order, you go from 4s into 3D. So the D block is always 1 minus the period number. So that means if I were to go into the next row, I'd have 5s, 4D. 6s, 5d, and so on and so forth. And then the final group that you'll notice, and I'm going to pinch this up and move it over, you'll notice that we have this bottom group here. This is known as the F block. Now, technically, the F block does not belong at the bottom. It belongs in here. So when we get to this point, you'll see that I have barium at 54 and then lanthanum at 55. So starting down here. So we would go 6s2, 4f14, all the way down to here. And then you go back into 5d10, and then you would go into 6p6. Again, it's a lot. We will definitely review this in class, but I just want you to understand, we can definitely read this like a roadmap, and it's so much easier when you do it that way. So the F block is 2 minus the period number. The D block is 1 minus the period number. The S and the P blocks are exactly the same as the period number. I know there is so much information in this last slide. Please don't be scared of that. We are definitely going to spend so much time talking about this like we always do. So if you have any questions, please make sure to ask me on Edpuzzle. But don't be discouraged if you don't understand this. You know that we will talk about this and work on it together. Have a good day.